Introduction to Ellipsometry and the Gartner Scientific Variable Angle Ellipsometer. Ellipsometry is a measurement technique that uses the polarization of laser light to determine film thickness. It's non-destructive and non-contact. It's a very useful method for measuring the thickness of materials that are transparent. It uses a linearly polarized laser light source that when reflected from the sample, it becomes elliptically polarized. Polarized light is light that consists of only light rays traveling in one plane. The polarization change or change in shape of the reflected ellipse is measured and film thickness is determined based on given information such as the incident and reflected angles and the index of refraction. The laser light passes through a polarizer and compensator before striking the film. The light is refracted as it enters the film, reflected off the substrate, and then refracted again as it leaves the film. It then passes through an analyzer, microscope, and finally photodetector. This unit contains the laser, polarizer, and compensator. On the right, the unit contains the analyzer, microscope, and photodetector. Down below is our stage, which will hold our sample, and at the top of the tool, an eyepiece, which is used to assist in stage leveling. Below the stage are 3 knobs for adjusting stage level, one for x-axis tilt, y-axis tilt, and stage height. These 2 knobs adjust the level or tilt of the stage. One is for x-axis tilt, the other is for y-axis tilt. To adjust the table or stage height, start by unscrewing this stage lock. Then at the back of the tool, use this screw to adjust to the desired height. When you're finished, be sure to lock the stage. The power switch for this tool is actually on the back of the tool and in the form of a key. Be sure to wait 15 minutes for the laser to warm up to operating conditions. Once the laser is warmed up, begin by placing your sample in the center of the stage and then opening the laser shutter to allow the laser to shine through. If you have to move your sample, be sure to close the shutter before doing so. Failure to do this could result in the laser beam being reflected into your eyes or another person's eyes, and this could result in retinal damage. On this tool, you have the option of taking single or double angle measurements. This is possible because you are able to select the angle of both the laser and the detector. To adjust the angle of the laser or detector, unscrew this locking pin, then pull out this bolt and slide it to the new position. Release, the bolt will fall into place, and screw back the locking screw. This tool requires some integrated software. Start by clicking on the GEMP icon. At this point, you should have the laser turned on and have allowed it to warm up for 15 minutes. The shutter should be closed. Your sample is loaded on the center of the stage, and you're ready to begin. Look through the eyepiece and use the X and Y stage level knobs to adjust the level of your stage. When you're finished with this adjustment, open the shutter on the laser. Now click on the 2 theta icon to begin taking a double angle measurement. A new 2 angle measurement and calculation table opens up. Here we can see our first and second angles at 70 and 50 degrees. To perform the measurement, we first need to tell the software what type of sample we're using. We can do this by clicking on Load New Model File. Our sample happens to be a thin film of silicon dioxide which was grown above a silicon substrate. So when we choose our model, we choose thin oxide. Among other things, this loads the known index of refraction here for thin oxide. But we also have to provide an approximate oxide thickness here. This is possible because oxides and many other thin translucent films appear to be different colors depending upon their composition and thickness. The reason for this is that the reflection of white light off of both the silicon below and the film surface above result in interference. As the oxide thickness changes, so does the interference, and thus the observed color. It's also important to note that the material will appear to be different colors depending upon your viewing angle. This is because decreasing your viewing angle actually increases the amount of material the white light has to pass through. So to approximate the thickness of a thin translucent film, refer to a color chart for the given film material, and always take your line of sight to be perpendicular to the sample surface. For our oxide sample on silicon, we estimated the thickness to be 1500 angstroms. Now we need to adjust the table height before measuring and doing our calculation. When we adjust the table height, as previously shown here, we notice that the table position indicator rises. And notice also to the left the Stokes power meter. The optimal Stokes power settings will vary for each incident angle and each type of thin film. When we're finished, we can click the Measure and Calculate button. Now it asks us to set the incident angle to 70 degrees. If you've done so, go ahead and click OK. Now it asks us to set the angle of incidence to 50 degrees. Make sure to change the detector and the laser to 50 degrees. Click OK. Now at the top we can see our measured values. Our first thickness around 1428 and our second around 1454 angstroms. Now, to perform a single angle measurement, simply click on this icon at the top of the screen. Now a new table opens up for single angle measurement, telling us that we're going to perform this at 70 degrees. Again, we need to load the file, thin oxide. Another way to do this is to click down here on the thin oxide hotkey. Once you've done this, we can put in our new estimated thickness, which is basically just the average of the first two thicknesses found by the double angle experiment. Again, we need to adjust our table height. Once we're satisfied, we can click OK, and now click on Measure and Calculate. The result is displayed here, 1428.42 angstroms. When we're finished with all our calculations, we can close the software, close the laser shutter, turn off the tool, and finally remove our sample. And that concludes our introduction and discussion of ellipsometry and the Gartner Scientific Variable Angle Ellipsometer.